Want to be sure to touch base and talk about dilution. So dilution is the process of adding extra solvent to an existing solution. So you take, say, you have something dissolved in 200 milliliters of water and you add extra water, so that we have 400 milliliters. You have diluted the solution. This leads to decreasing the concentration of the solution. You get to a more dilute solution. This is extremely common in the lab for preparing solutions. If you want a particular concentration or you want to do some process, you want to lower the concentration somehow. You want to not just randomly add extra solvent, but adding particular amounts of solvent. So that way you get to a new lower concentration. In the chemistry lab, usually when you buy like a solution or buy a chemical, they come in solutions. They come really concentrated. We call them stock solutions. They're usually really concentrated. So for example, HCl, hydrochloric acid, when you buy it, it comes in a solution that's 37% hydrochloric acid. That's a lot. It's a high percentage. That's not what we commonly use. And so, that's the idea is it's cheaper to basically buy it really concentrated, and then you can dilute down to whatever you want, as opposed to having to buy like a huge volume of say like 1 molar HCl, and then you can't make it more concentrated. It's also pretty common in like, especially in biology or in any sort of science, if you're trying to analyze a mixture. So say you're trying to analyze a mixture, so you have to like say a mixture of bacteria, and you try to know like how much bacteria is in there. When you go to like plate it out, you just get like a ton of colonies and you can't measure it out. So what you do is you do like a known, you call it serial dilution, but you dilute in like a known way. And so you can figure out then, in this more dilute solution, you can then, the number of bacteria is low enough that you can start to count them. So you can like count the concentration of bacteria in the dilute solution, and then you can like do math backwards to figure out what the concentration of the original solution was. So, you're kind of doing that idea going backwards. And so that's kind of, dilution is really common throughout science. In all honesty, if you are going on to pursue any sort of lab science career, dilution is the most important thing you will learn in general chemistry as a useful sort of approach moving forward. When you're working through dilution, it's all about based around the dilution equation. So you may have seen this equation or something similar. C1 times V1 equals C2 times V2. Basically, each side of the equation is a concentration times volume. We've seen throughout this chapter that when you multiply a concentration by a volume, you get something that is the amount of solute or something close to the amount of solute. And so this can be any concentration unit that has volume on the denominator. So just not molality. The only thing you can't use is molality. But everything else will work. As long as your concentration unit is the same before. So this capital C here, this means concentration. So you may have seen this before with capital M's for molarity. That's commonly used in chemistry. We are commonly using molarity, but you can do dilution you can use the dilution equation with any concentration unit as long as it's the same on both sides. And then that subscript 1 and 2, that just corresponds to like which solution you're talking about. Usually 1, the 1 is the kind of pre-diluted, more concentrated solution, and the 2 is usually diluted solution. It doesn't really matter as long as you're consistent. So C2 and V2 need to both be after or before the dilution. So let's look at an example. Saline must be at 0.90% weight by volume for use in humans. You have a 2.00% stock solution. How do you prepare 10.0 milliliters of usable saline from your stock? So we can see this is a case where we are using dilution you're trying to make a solution. We want to know how can we prepare it. We're going to do it via dilution.
Saline must be at 0.90% weight by volume for use in humans. You have a 2.00% stock solution. How do you prepare 10.0 milliliters of usable saline from your stock? So when we look at this, when you think about, this is a pretty common situation in the lab where we are asked, how do you prepare something? How do you prepare a solution? And so what that means, what we want from this, our answer should be a recipe, right? It should be a set of instructions, a recipe, a protocol for how to do that preparation, how to make that solution. 10 milliliters of usable saline, so it needs to be 0.9%. And so we've seen kind of problems where we're dealing with molarity, where you're dissolving solid or dissolving your solute into the solution, so you can figure out how much you need and things like that, how much you weigh out the mass. But this is slightly different because when we think about it here, the difference is the information that we're given is that we have a stock solution, right? So when we're given information on a stock solution, that is a good sign that we are going to be using dilution, that we have some sort of more concentrated solution that we're going to add additional solvent to produce a more dilute solution, our lower target concentration. So you can see that not only do we have a target concentration, we also have a target volume. So this would be the end. These are the kind of target, this is the goal of our dilution. 10 milliliters of 0.90% solution. So when we are ever dealing with dilution, we want to use our dilution equation. C1 times V1 equals C2 times V2. C stands for concentration, V stands for volume. So we want those variables to be filled in. And we can see we've got, you need 4, 1, 2, 3, 4. There's a total of 4 variables. If we want to solve for 1, we need to be given 3. So 1, 2, 3, we do have those 3 variables. We can solve for the 4th unknown, or the single unknown, the 4th variable. And so we can kind of go through the process of assigning those. One of the things that we want to check is, are our concentration units the same? That's good. Dilution, the dilution equation, we can just plug them right in. We say that this is the 0.9% is the use in humans, 10 milliliters of usable saline. So those two are going to be paired together. That is a single solution, 1 or 2. Because it's the goal, normally we would make that 2. So we would then come in and say that C2 is going to be the second concentration. So that's going to be my 0.90%. V2 is going to be my 10.0 milliliters. So stock is then normally solution 1. And I have only a concentration there. 2.00% is that concentration of my initial pre-diluted solution. And so what we can do is just plug all those numbers in. So when we're looking at our units, those percents are the same. That checks out. We have milliliters here. Previously, we've seen that we would need to potentially change those into a particular unit, but it doesn't matter when you're dealing with dilution. Whatever this unit is, that's the unit you're going to get out over here. So as long as this can be milliliters, gallons, whatever you want, you just need to be consistent between the two volumes, V1 and V2. So do some algebra. V1 is equal to 0.90% times the 10.0 milliliters divided by this 2.00%. We can see that those percentages cancel out. Only thing that's left is those milliliter units. 0.9 times 10 is 9 divided by 2. V1 is equal to 4.5 milliliters. So we got our number. But is that what we wanted? If we go back to our question, how do you prepare? right? How do you prepare this solution? We have a number here. We have a V1. Of this stock solution. So how we would write out this recipe is if we think about actually doing the dilution, we would say step 1, get 4.5 milliliters of your stock solution, and that's the 2.00% solution. So that's step 1. That's the information that we got right here. The V1 goes right there. So we have our stock solution. Now you need to dilute. And we dilute by adding extra solvent. So you would say you add water. Now, a lot of people would kind of say, well, you're at 4.5. You need to get to 10. So in order to do that, you could take the difference, 5.5 milliliters. But that's not quite right. Volume is not additive. You don't add 5.5 milliliters. Instead, you add water to reach a total volume of 10.0 milliliters. It's not going to be, it's going to be close to 5.5, but it's not going to be exactly 5.5. It's probably going to be a little more here because the solution ends up contracting or expanding. The molecules get closer or further apart as the concentration changes. Volume is not additive, so you don't even need to say, you just add water. You add enough water. You'll see enough used here a lot. Add enough water to reach a total volume of 10 milliliters. It's a little janky. Total volume of 10.0 milliliters. And so this is the recipe, because we want to actually know, how do you prepare? We're actually designing ways to make solutions, and here's how we do it.
Let's do one a bit more complicated. Hydrochloric acid is sold as a 37% weight by volume solution. How do you prepare 100 milliliters of 1.0 molar HCl from this stock?
Hydrochloric acid is sold as a 37% weight by volume solution. How do you prepare 100 milliliters of 1.0 molar hydrochloric acid aqueous solution from this stock? So again, how do you prepare? We are looking for a recipe. And again, we're pulling from a sold as this solution, right? We are given a solution and I want a different solution, okay? And that different solution has a target volume and concentration. Okay, so this would be where I start. And this would be my goal. And so all of these ideas of target, your starting solution, your goal solution, all point to using, again, my dilution equation, where my start is going to be solution 1, my goal is going to be solution 2. C1 times V1 is equal to C2 times C2. This is my my starting solution. So 37% times volume 1, which I don't have, becomes 1.0 molar times 100 milliliters. And so we can see that we have an issue. That's concentration, or percent, and that's molarity. Those are two different concentration units. That means if we just divide out 37%, those will not cancel and we won't get a good number, right? We won't get a useful value. The dilution equation won't work. So what we are going to need to do is a conversion. So we're going to convert between these units, these concentration units, make them the same. What I'm going to do is I'm going to take the 37% weight by volume and turn that into a molarity. So I need to do my unit conversion, my concentration conversion. We've seen that before. So I have 37% weight by volume. That is the same thing as having 37 grams of HCl for every 100 milliliters of solution. And then it'd be times 100, but that one doesn't really matter. Well, we have set up our ratio. This is how you could prepare a 37% solution. I've got a numerator value and I've got a denominator value. And what I want, my goal, is a molarity that would be equal to mole of HCl over liters of solution. So I'm going to need to take this grams of HCl, turn it into moles of HCl, and you take this milliliters of solution and turn it into liters of solution. So I'll start with my numerator. Amount of solute. I have 37 grams of HCl. And what I want is I want to turn that into moles. So I'm going to need to use my molar mass that I've seen previously. Do that conversion. You can calculate it or look it up. The molar mass of HCl is 36.46 grams of HCl for every 1 mole of HCl. And that comes out to, when we round to sig fig, that becomes 1.0 moles of HCl. So I set up the solution, set up a sample, took that amount of solute, and just changed the units into moles. Now I'm going to take the denominator. I have 100 milliliters. I want to turn it into liters. That's my volume unit by definition for molarity. So 1,000 milliliters for every 1 liter, I get 0.1 liters. So I've taken my 37 grams, turned it into, that's equal to 1 mole of HCl. My 100 milliliters is equal to 0.1 liters. And finally, I'm going to combine them. And I get that my molarity would be equal to 1.0 molar, or moles, whoopsie, of HCl divided by 0.1 liter. And that would be 10 molar HCl. And so also points to one of kind of the silliness of concentration. People talk about stock hydrochloric acid as being 37% weight by volume. And if you look at that, you think that's kind of a random number. Why is it 37% weight by volume? That's just another way to say the much more kind of round number of 10. Stock hydrochloric acid is 10 molar hydrochloric acid. So stock is very concentrated. This is really nasty stuff. So it is 10 molar hydrochloric acid. But because it's like a product that's sold and kind of for some old-timey reasons, we just call it 37%, even though the much more chemically relevant value is 10 molar. So sometimes you will see it sold as 10 molar stock HCl, but a lot of times it's still called 37% for whatever reason, even though it's just 10 molar. 37 is not chosen randomly. It is instead chosen because that is the same as having 10 molar HCl, which then is kind of, you could see 10 being much easier to think about dilutions in, and much more useful. It's not randomly just like, oh, we just sell this at this concentration for whatever reason. But we're not done. We just did the conversion. Now we want to go back to the actual dilution. Okay, so it was our dilution setup. We did have 37% times V1, 100. That 37% we can just replace with the 10 molar now. So I'll go ahead and rewrite C1 times V1 is equal to C2 times V2. So then it would be 10.0 molar times V1, which we don't know, is equal to 1.0 molar times 100 milliliters. We just divide that 10 now. V1 is equal to 1.0 molar times 100 milliliters divided by 10 molar. V1 times 100 is 100 divided by 1 would give me, divided by 10, sorry, is 10. If we look at our units, those molarities are going to cancel out. That was the whole point of doing that conversion. And we're left with milliliters. You know, normally when we talk about like molarity, if we're working with the molarity equation, everything needs to be in liters. But with dilution, it doesn't matter. We can just leave it in milliliters. So we can use our dilution equation, kind of figure out what this would be, or what that initial volume should be, that V1. So you need 10 milliliters of the concentrated. But again, we want the recipe. So we do need to write out how we would do this, because we want to think about if you're in the lab, you would need to actually do it now. So step 1, get, what was it? 10 milliliters of your stock, 37% weight by volume solution. And you'll notice I'm using the original concentration, the label, because that's what's on the label, right? So you're giving instructions to someone else, potentially, this recipe, and you want to give them what the name or on the bottle should be. You already did the work for the conversion, so you're just given the recipe, but you don't need to say it's the 10 molar, because someone went in the stockroom, or in the, like the kind of storage, it would say 37% solution. So 2, we'll use this time, we'll throw it in, add enough water to reach a total volume of, what was it, 100 milliliters. And again, that word, enough. It's going to be not, you're not going to add 90 milliliters. 10 molar HCl is very concentrated. It's doing some funny things in that solution. You're going to need to add more than 90 milliliters. Because there's going to be some chemistry going on that we'll get to later this semester. So you want to be sure you're always saying it's just add enough water to it, and that's how you would actually do the how do you prepare is right here. 100 milliliters of the stock solution, add enough water, reach a total volume of 100. And then the concentration will be 1 molar.
That's it for chapter 11. You kind of will note that this is the like recap or the skills, and it seems like there's very few of them relative to, say, chapter 10, which is huge. One thing, it's only been 2 lectures, 2 sets of videos. Another thing to know is that some of them are pretty bulky, like all of concentrations is just in one thing. So there's a lot in there, you know, like solubility of ionic and covalent pactins. So there's a lot. These are very dense. These are each one is quite a broad set of skills. Chapter 10 is a bit more kind of pick and choose focus, but you can use this to start preparing for tests, kind of review when you want to kind of be looking back holistically on chapter 11, kind of a summation of the most important things, and not just most important things, but what you should be able to do with those important ideas. Okay, 3 questions on participation 127. You want to find all 3 of those questions, get them answered. and get those answers submitted over on Blackboard by Tuesday evening. Midweek 3 homework due Wednesday. We'll cover this first set of videos. For lab on Wednesday, we're going to start in room 141, the classroom where we move after lab usually. We'll start there. We'll meet at 11 o'clock. We will do the chapter 10 participation quiz, which is going to be 20 minutes. Then we'll go start heat diffusion of water at 11:20. The pre-lab technique and notebook are all still due at 11 a.m. Those are still due at the start of the lab period, even though we're going to not do the lab until 11:20. Otherwise, we will have a normal second half of this week. Participation due Friday. We'll start chapter 12. It's a cool one, very different than probably anything you've seen. We'll start that, chapter 12, kinetics, but otherwise, the answers to this participation go live Tuesday night. Otherwise, I'll see you in lab. Enjoy the rest of your day. Bye-bye.